Welcome to the Level 3 video on ordinary differential equations. In the last video, we were looking at eigenvalues and eigenvectors, and we're going to use these now to solve a first order linear system. The system is dx by dt equals 15x minus 35y and dy by dt equals 6x minus 14y. First thing we have to do is formulate this as a matrix, and we can do this in the following way: by taking the t derivative of our solution matrix x bar is equal to a 2 by 2 matrix, the coefficients the same as above, 15 minus 35, 6 and minus 14, all multiplied by our solution matrix x bar. X bar is x and y. Then, if we apply matrix multiplication to this, we'll end up with a system exactly above. So the first thing we want to do is diagonalize the 2 by 2 above. Let's call it m. 15 minus 35, 6 and minus 14. We do that by calculating P inverse times M times P, which is equal to D. But we know how to calculate D, P and P inverse from the level 2 video. So if you're struggling to remember how to do those, just refer back to the level 2 video. Here's a quick summary. D is the matrix with diagonal entries, which are the eigenvalues, lambda 1, lambda 2, all the way to lambda n. In this case, n is just 2. Our eigenvalues were 0 and 1. And P is the matrix whose columns are the eigenvectors v1, v2, all the way to vn. Of course, n is still 2. So it's the 2 by 2, 14, 6, and 15, and 6. And P inverse is just the inverse of this matrix above, so 14, 6, and 15, and 6. And calculating the inverse of this, which is 1 over the determinant, 14 times 6 is 84, minus 19, which is 6 times 15. Multiply this by 6, minus 15, minus 6, and 14. And this gives us minus 1, 5 over 2, 1, and minus 7 over 3. So now we know the diagonalization M equals P, D, P inverse. It just remains to solve. The derivative with respect to t of x bar is equal to p to the minus 1 x bar, because originally it was m x bar. But now we have a diagonalization, we can replace it with p, d, p inverse. Multiplying this whole equation by P inverse yields the following: P inverse times the derivative with respect to t of x bar, but P inverse is just a constant, so we can actually push it through the derivative to get the derivative of t times P inverse times x bar is equal to the right hand side, which is P inverse times P times D times P inverse times x bar. Now, using the substitution, which is very important, P inverse times x bar is now equal to y bar, and let's call y bar y1, y2. It remains to solve the derivative with respect to t times y bar is equal to capital D times y bar, which is 0, 0, 0, 1 times y1, y2. So for simplicity, let's multiply this out. So we're going to have the derivative with respect to t times y1 from the left hand side is equal to 0 from the right hand side, which implies that y1 is a constant, let's call it c1. And the other equation we're going to get is the derivative with respect to t of y2 is equal to y2, which implies that y2 is some constant times the exponential of t. Then we need to go backwards and multiply our substitution by p. So if p times y bar is p times P inverse times x bar, this is of course equal to x bar, because here we have the identity. So x bar is the matrix 14, 6, 15 and 6 multiplied by y bar, which is c1 and c2 times the exponential of t. So our solutions are the following: x is equal to 14 times c1 plus 15 times c2 times the exponential of t, and y is equal to 6 times c1 plus 6 times c2 times the exponential of t. Thanks very much for listening.